Hello, Homer White back again. Third in our series of screencasts on normal distributions. So this time we're going to talk about percentiles for normal curves. So, concept of percentile rank. Let's go back to imagining our population of college men, where the mean height is 72 inches and the standard deviation of the heights is 3.1 inches. Just imagine millions and millions and millions of college men. And their average is 72, the standard deviation of their heights, 3.1 inches. And suppose the heights are normally distributed so that if you made a, like a histogram of all the heights, it would look like one of these perfect bell-shaped curves. Suppose we want to know the height of a man who is taller than 80% of all the other men. That height that we don't know yet is called the 80th percentile of the heights. The height where 80% are below is the 80th percentile. In pictures, it would look like this. Got this normal curve, giving the distribution of the population of these college men's heights. 72's right here in the middle. And there's this number x that we don't know yet. But the area underneath the normal curve before this blue line over the x is 80%. That unknown number is the 80th percentile. So when you are asking about a percentile, you're actually asking the reverse of a probability question. In a probability question, you know this boundary number and you don't know this area. And that's what you use Qnorm GC for. But in a percentile question, you know the area, you just don't know the boundary number that would make that area. And so we need a way of answering that kind of question for normal curves. So what you use is a function called Qnorm GC. Q is short for quantiles, which is another word for percentile. The syntax for it is very similar to Qnorm GC. You say Qnorm GC, parentheses, because you're using this function. But your first input is that area that you know that 80% or below, so you say 0.080. It's 80% or below, so you say region is below. So R knows that you're talking about this kind of area before a number. And then your next inputs just give you the mean and the standard deviation for the normal curve that you're thinking about for your population. And here you are asking for a graph to go along with the answer. So let's copy, paste, and give this a try over in our studio down in the console here. And here's our answer. So the title is saying that we're looking at a normal curve with mean of 72 and standard deviation of 3.1, and that we're asking for the 80th percentile. The answer is down here. It's this number, 74.61. If you want to be taller than exactly 80% of all the guys, you need to be 74.61 inches. That's the 80th percentile. So here's the same thing over in the slides. So if you want to interpret a percentile in a simple sentence, then you might construct a sentence like this one. You might say that a 74.61 inch tall male is taller than 80% of college men. You could say it more technically, the 80th percentile of the heights of college males is 74.61 inches, but this first sentence is what you might use to explain that concept. Another example, can we find the height of a person, can we find a height so that a person with that height is shorter than 10% of college males? So let's think about this. If 10% are taller than our person would have to have 90% shorter than him. So our person would be at the 90th percentile. And so you could say Qnorm GC, percentile is 0.90, region is below. Same mean, same standard deviation as for a graph. And you get this result. The 90th percentile is 70.97 inches. In the console in our studio, it'll give you a little bit more precise figure if you like. So here's a little tutorial for Qnorm GC. If you were to follow this link, you would come to this tutorial. Again, it's part of the TigerStats webpage, and so you can get to it from the home page by going to vignettes and then looking down for Qnorm GC. Another concept I'd like to talk about in this screencast is Z-scores. So the Z-score is a number that you compute off of a particular data value. And so you might take a certain person's height, maybe, call it value. Subtract the mean height for the group. Divide by the standard deviation of the heights, and you get a Z-score. So it's called little z for short. Now let's think about this. The numerator, value minus the mean, is how different your height is from the mean height. When you divide by the standard deviation, this ratio here is saying how many standard deviations that value is above or below the mean height for the group. So good to remember this. Z-scores tell you how many standard deviations a value is above or below the mean for the group that value is associated with. Now, we're interested in Z-scores for a lot of reasons, ultimately. But for now, I'm going to suggest that you just use it as a guide for deciding how unusual a value is, how unusual the value for some random variable is. Remember that when a distribution is roughly normal, about 95% of the values are within 2 standard deviations of the mean. That's that 68-95 rule. So only about 5% are outside this range. So if we could just go back to our studio for a minute, I'm going to ask for imp rule GC mean equals 0, SD equals 1. And oops, I'm sorry, I have typo. There we go. And let me take away my picture. So what I've got here, the number 0 just stands for right in the middle. You're 0 away from the mean. The number 1 stands for your 1 standard deviation away from above the mean. And the -1 stands for your standard deviation below the mean. Let's go to mean plus or minus 2 standard deviations. Okay, so 95% are within 2 standard deviations. Let's go for outside. That 5% that's outside divides equally into the 2.5% that is 2 or more standard deviations below the mean, and the 2.5% that are 2 or more standard deviations above the mean. So what this is telling you is that if you have a z-score that's bigger than 2, like here, that means your original value was unusually large. It was in the top 2.5% of all the values in that group. If you get a large negative z-score, like if you get a z that's less than -2, then the value was unusually small. It was in the bottom 2.5%. Let's take a look with some actual data. Justin Verlander, the pitcher, throws different kinds of pitches, but let's just look at his four-seam fastballs. So we take the Verlander data set that we've looked at before and we pipe it into this command called filter. And we're just going to pick out the rows where the pitch type is equal to quotes FF, a four-seam fastball. So let's make that data set. Copy into RStudio. I'm going to make this a little larger for you. Paste. And here's four-seam. So it's about 6,700 pitches that were four-seam fastballs. Now let's make a density plot of the speeds of those pitches. And there it is. It's a roughly bell-shaped density plot. So we could model Justin Verlander's four-seam fastball's pitch speeds with a normal curve. But we need to use the normal curve that has the mean speed of all those pitches and whose standard deviation is the standard deviation of all those pitches. So let's calculate the mean. And if you were to run the mean function in RStudio, you'd get about 96 miles an hour. And if you guess for the standard deviation of the speeds of the pitches, then you would get about 2.03. Notice I'm using four-seam as my data, not Verlander, because I just want the mean and standard deviation of the four-seam fastballs. Okay. So mean speed of Verlander's fastballs is about 96 miles an hour. Standard deviation of the speeds is about 2 miles per hour. So now we can think about individual fastball pitches that he throws and get an idea of how unusual they are in terms of their speed. What if he throws a 99 mile per hour pitch? That's an above average speed. It's bigger than 96. But how unusual is it really? Well, get the z-score. The value, 99, minus the mean of all the pitches, 96. That's a 3 on top. Divide by the standard deviation of 2. 3 divided by 2 is 1.5. So a 99 mile pitch is faster than average, but it's only about 1.5 standard deviations over the mean. I would not call it unusually fast. On the other hand, suppose he throws a 91 mile per hour fastball pitch. How unusual is that? Get the z-score. 91 minus 96 is a -5. Divide by the standard deviation of 2, you get -2.5. There's a z-score that is less than -2. So we're looking here at an unusually slow pitch. That's how you use z-scores to figure out how unusual a data value is compared to everything else in the group that it comes from. Last thing, I just want to mention a particular normal distribution. I actually drew a picture of it when we last used Qnorm GC. It's the one where the mean is 0 and the standard deviation is 1. Now, here's an interesting fact. if you take any normal random variable, call it x, so it could be normal with some mean mu and some standard deviation sigma, okay? And if you define a new random variable by this fraction here, random variable x minus the number mu divided by the number sigma, that's a random variable too, because it depends on x, which is a random variable. Well, z is like the z-score for x, right? Turns out, as long as x is normal, its z-score random variable is going to be normal with a mean of 0 and a standard deviation of 1. So that's a fact that we're going to make a lot of use of later on in this course. It's such an important distribution, the normal with a mean of 0 and standard deviation 1, that we call it the standard normal distribution. And we'll use a capital Z to represent it as a random variable. That's it for now. See you later.